telescope that would allow really new science and that will be proposed as the next ISO big project after ELT. So why ELT is not yet there? So why it's pressing to think about the next? The main point is that for ELT, from the start of the discussion to the first slide will be 30 years. Okay, so we know that this big project takes a long time, first to make the community to agree what should be the next, then to find the funding, everything. So we cannot do things in sequence. We must think in parallel. So I think that, and the time is appropriate because the ELT is now shaping quite well, and it will have first start in 28. So I think it's really time to do that. Okay. So you see, Italy is a significant partner of this project with quite a number of institutes, and you are there. So this, let's look to the landscape rapidly. So the landscape will be really a lot of things to do. So you all mostly are concerned with many of them. Euclid, I'm sure you are quite interested in what's coming out from Euclid, SKA, DLSST, ELT, and so many others. Most of them have very big imaging capability, wide field, high resolution. So there will be in the coming years, in the coming decades, a deluge of high quality image all over the sky. That would be great. But nevertheless, to understand the millions of sources that will be discovered, there's no escape. We need spectroscopy. We cannot do everything with imaging, and this is needed to characterize the source. But it's going to be a fantastic challenge to meet that. If we just take the number, for example, from the LSST, we expect 20 billion galaxies and 17 billion of stars at the end of the 10 years nominal survey. That probably will go on. And really doing that, only a fraction of that, we need really a spectroscopic dedicated facility with a large aperture. This is, I think, something really needed. And of course, we are not waiting to look to this. And so we have started to develop new multi-object spectroscopic facility that are dedicated and use the 4-meter class telescope, which are refurbished to do that. So we have DAISY, which is now working quite well. Foremost, that will be probably in 1 year from now, starting operation, and WEAVE probably at the same time. So, however, these are 4 meters. So 4 meters means that only a very small fraction of the source, the faint source, can be done. There are, of course, new MOS instruments that will be installed on existing 10-meter class multi-purpose telescopes, such as PFS at Subaru, MOS at the VLT. This is great, but currently their multiplex capability is relatively limited, and also they have to share the focal plane with other instruments, so are not dedicated. And so I think there's a need. Just to mention that the upcoming giant telescope, because of, they have intrinsically, because of, let's call it étendue conservation, a small field of view. And so, and relatively small multiplex with huge instruments. So they will do something completely different. But if we're keen to obtain large sample of faint sources, there's no way we will do that with coming large telescope. So there is clearly a strong need for a facility. This is well known, and this is in discussion since now quite a number of times. So a new facility with a very high multiplex MOS will be really something that is needed. In parallel to that, and this is a bit more new, there have been the development of integral field spectroscopic surveys. So they address a much smaller field of view. But given the very high sensitivity of this instrument and the, in a way, extremely high multiplex, because you get spectra all over the field of view, these are complementary to MOS survey. And I will just spend 1 second to show how it can be. Because on the other hand, if you look, the MOS have an extremely large field, so you select the source on the large field, and you can maybe ask yourself why you can do something interesting with a very small field of view. So when I proposed MUSE a long time ago, there was a lot of skepticism that it will work. At the end, I think we show it works. I just show as an example. It's on the very well-known Chandra deep fields far south that have been observed by the MOS with almost 20 years of observation, because this was, and I think this is still the deepest image ever obtained in the sky by Hubble. And the spectroscopic good quality source that I've been able to obtain is relatively modest to the number, compared to the number of sources that you can get it in the deep images. You can see the number here in the red. And you can see more or less, you see the state of the art. So the redshift distribution peak at around 25, 24, something. And that's for the magnitude, and the redshift distribution is mostly peak at around 3. Okay. On a much smaller field of view, which is a very small fraction, we have been able in a limited number of time at the VLT to obtain a very different redshift distribution and very different magnitude distribution. And this is because it's a bit interesting. Here we are addressing high density source, very faint, where you will not be able to put a multi-object because they're just too faint. And it's crowded, and then the MOS become extremely inefficient to do that. And then it has really opened a new way to do a spectroscopic survey. And this is very complementary because with the MOS, you get the large scale by definition, and the bright end, the luminosity function in that case. And with the panoramic spectrograph, you get the small scale.
And London King's Cross. The next station is Finsbury Park.
Was it a comment or not? Anyway, so of course, if you have integral field spectrograph, I think the thing is you don't do preselection. You can, of course, discover new source. And this is what has been shown here. You show the magnitude distribution of the source. There is a peak at magnitude 30, which just show that we are able to detect a large fraction of sources that are beyond the limiting magnitude of the ultra deep fields. So beyond magnitude of 30. Just explain, this is really very faint galaxies that are very with a high star efficiency, star formation, and that are just detected by their Lyman alpha emissions. But of course, you can also do something which I think is more interesting, is not to get the galaxies that are surrounding. And we know that if we need to understand galaxy evolution, we need to understand them in their context, see how the flux of matter comes in and out and all these sort of things. So you can do that at different scale. And if you push far enough, and this is the sort of ultimate experiment we did with MUSE, we push to more than 100 hours of exposure, then you are at a level where you can detect the diffuse emission of the filament itself. So I think it's something interesting. So if you can imagine that you can do that more easily with a better instrument, I think then you can really do something complementary to the large-scale structure, and you will do with the MOS. And of course, since you don't select, serendipitous discovery, because you get spectra of everything. But of course, getting a much bigger instrument than MUSE is going to be difficult on a telescope. You can see the image here on the right, which is the MUSE. You see, feel completely the NASPIS platform of the VLT, which is one of the biggest NASPIS platform of the 10-meter class telescope. And having something, let's say, 10 times bigger, this is what it like, would be unfeasible with the current scheme. So at the end, I think WSC, this is really the combination of the two. Proposal to join the two complementary approach by building a dedicated facility with a very advanced MOS and a giant panoramic EFS, both working at the same time. And this is what we like to do. And we know that spectroscopic survey have provided a wealth of information on sources, and SDSS has been a fantastic example, 2DF, gamma, etc. But also in EFU spectroscopy, when are just starting, I've also provided. If you can join the two, I think there's a lot of science, key science to be done. So this is something which is, as I said, on the idea of the committee since a while. And for example, the Astronet roadmap really sees that as one of the first priority of a ground-based facility that is missing in the global landscape. This is also in other plans like Astro 2020, Australia, long-term plan Canada, and many others. So we have started to think about what we can do, a sort of mixture of dream and reality, what is feasible and so on. This is always a difficult exercise to find. So we came up with a very ambitious top-level recommend, but we think should be feasible. So it's a telescope aperture, will be a 12-meter, seeing limited, with a very wide field of view, the largest that we can do, and you will see later on how big it is compared to the current telescope we have, with a spectral range covering the visible and the near-infrared. And there will be two instruments. The first one is a multi-object with two modes. The low-resolution mode, which is extremely high multiplex, 20,000. As a comparison, I think Foremost has 2,000. It's really another of magnitude, bigger, with a medium spectral resolution and a spectral range which cover the visible range simultaneously. So you get everything first time. Why not the infrared? The infrared we see is today a bit difficult for a number of points that I could detail later on. So we foresee as something to be done on a later stage. And there will be a high resolution mode with a very high spectral resolution, 40,000, lower multiplex, of course. And they will not cover the full spectral range, but a few windows that's mostly dedicated for galactic studies, as you can think of. And then the second instrument is this monolithic EFS, a sort of MUSE-like big instrument, with 9 times the field of view of MUSE, and which cover the full spectral range in one go. So it's a sort of combination of MUSE plus blue MUSE that is currently studied that will cover the blue. And you can also cover a wider area. I will show in a minute why. And there is 2 operational requirements which are key. The first one is that we want the MOS and IFS to be operated simultaneously. And you will see this open very interesting opportunity. And the second, because we think that target of opportunity will be absolutely key with the advance of time domain science. We want to build that from scratch on such a facility. So to be implemented at telescope and fiber level. So this is what we have, and just show here the field of view. So you can see here the field of view, that's 2 degrees. 2 degrees for a telescope which is twice the aperture of the VLT in area. It's extremely big, and you can compare to the VLT field of view or even to the LT. And then in the center, while you are doing multiple configuration with MOS, you always have to do because you have to deal with the clustering of sources. So you do multiple exposure. At the same time, you can obtain interfield spectroscopy with the red part, which is a 3x3, which is much bigger than MUSE itself, which is itself much bigger than other EFS. But you can still, maybe, because it will go faster, probably, you can mosaic and go to a much larger field of view or go much deeper. So that offers the flexibility to do that. So you have, of course, you do the traditional exercise to compare to others and show that you are doing much better. But in that case, it's not very difficult, I think. So compared to, for the MOS, you use the telescope aperture, so very faint, and the multiplex, and the key number. And you show that WST is really standing above here. And because it's at even a wider field of view, a larger aperture than that, and wider field of view than the other, that's Mega Mapper or MSC in the north, it has a larger étendue. So the étendue is this proportional to the circle. So it will go faster. Okay. And you can see here clearly that why I think ELT are not competitive for that size. Right. So the ELT are here, the mosaic, manifest, because of course very big aperture, but our multiplex is very small. And on the, if you look to the EFS, then I think there's probably no competition at all. The field of view is so much bigger than all the existing. Again, the ELT1 Harmony IRS will do extremely high resolution, but a small field of view. So it's quite unique. And the combination to these two is completely unique. So we see the research as a facility. The facility is not like a general purpose telescope. General purpose telescope, you design the telescope as much as you can, and then with the money left at the end, which is relatively small, you put the first generation of it. And this is what happens with the LT currently. So most of the money go into doing the telescope that costs at the end more. But it's not a problem because there will be second, third generation and so on. So I think it's okay. So you design the telescope, you put all your money in the telescope, more or less. In the facility, no, it's not the same, of course, because you have to design all together. And so instrument and telescope are designed all together, and so the criteria is what maximize size. And WST probably will go, we have not the detail of the cost yet, it's part of the study, but we can expect that the cost of the instrument will be at least half of the cost of the total signal, probably more than the telescope itself. So we have a design. So it looks like that. So the telescope is a Cassegrain configuration with a mirror which is segmented. And the segments are exactly the same size as the ELT. Of course, the prescription is different, but and so we can reuse all the technologies that have been developed for ELT. And this is, of course, very important because a lot of money went by ISO to develop this. Then on the focal plane here, you have a field corrector and an atmospheric dispersion compensator that is there that sends the light with the correct F ratio to the multi-object, which then there is the fiber positioner with the 20,000 fibers. And they are sent to the MOS instrument, for the moment currently under design, so not yet done, which will be located into the azimuth platform to limit the size of the fiber, especially for the blue throughput. I think it's important. And then there is a fraction of the center field, which is sent by a combination of mirror through the Nasmith CDFS relay, which you can select the field, the 3x3 arc you want, which is sent down the telescope to what we call the EFS station, which is a gigantic sort of a wall of spectrograph with 144 spectrograph, each having 2 channels. And so you understand here why it's not visible with the current telescope. You have to, more or less, you design things all together so that can fit. So into the ESO context, it looks like it's not as big as the LT, but it will be definitely a bit bigger than the VLT, but it's a relatively compact design. And we will locate it in Paranal. And this is the place which belongs to ESO, the VLT, the ELT there. And one side that we're looking, which looks promising, is L'Aquila. Why that one? Because it doesn't need further negotiation if we were outside with Chile, because it's part of ESO, and it's also far away enough from the VLT and ELT, so we don't have problem with the laser collision, because we operated in visible, and ELT and VLT will have a lot of laser. And the main reason is not to have a new site, is sustainability. Of course, sustainability is going to be a key factor to develop new facilities. So it will be really something we need to look carefully. And of course, having not to develop a new site, you gain a lot. You can also use the Paranal solar plant to provide energy. And so this is an important item we are looking into. Science case. So science case is white, like the field of view. And cover a lot of different science that go from the galactic, resolved stellar population, extragalactic cosmology, and time domain. And so all these use facility either with a MOS, low resolution, high resolution, IFS, often a combination of the two. And so I'm not going to describe everything. So you have a white paper, the version 1, there will be a version 2 later on, with you can look to this, quite comprehensive, and you can look to it. I will give a few examples. But what I want to stress here is that WST is not just you work in synergy with other facilities, like most facilities does. By having WST in the global landscape, it will enable new science that will that the existing facility cannot do alone. This is obvious. SKAO, for example, they don't have the redshift. LSST, also, but more later on, the Einstein telescope will need such a facility to fund the gravitational, understand the gravitational wave event, and so on. So this is really something which is specific to WST, is that it's by this multi-billion facility, you will enable new science. So I'll give a few examples, just a glimpse. So that's start with galactic science. Here we're mostly the key for this science is multi-object high resolution. So having both a very large aperture and a very high spectral resolution, 40,000, you can do a lot of interesting things. You can get full chemical information and abundances, radial velocity, up to really faint source. And this show what is currently what you can do. So that's, I think that's a Gaia spectroscopy, which is sort of reference. So with 4 MOS, you will extend this to sun main sequence. And if you go to the red curve, you go much further, but you see it's still limited in the galaxy. Going to a larger aperture, of course, you extend that considerably. the main sequence, and you can cover the whole galaxy with the red giant. So you can do very interesting stuff. And origin of the stars and the Milky Way systems, neutron capture, so source of the neutron capture element, star formation, chemical clocks to measure the stellar age with the chemistry, stars and planets to understand in a big statistical way the role of stars that have planets and those that don't have. Evolution of stars, what dwarf, and so on. So a lot of things can be done. I just show here in this animation what is the impact of the line detectability, how you can measure abundance of much more elements if you get to higher spectral resolution. And this is very clear, and this is something that we will get from WST. Second example, I think here. Here it will mostly use to dance systems, stellar systems. And so you can do a lot of things. Here you will mostly use the integrated spectrograph because this is more related to get the stellar clusters or nearby galaxies, which can be resolved. And you can study the population of massive stars, for example, in the metal poor galaxies. And you can do the role ultra-faint dwarf in galaxy evolution. Amazing. The idea you just point with the EFS, the center of the galaxy, and then you can use a high resolution to the brightest star in the surrounding, to get complementary information. Going more on the extragalactic science case, there's just one example which I think show beautifully how we can reconstruct the dark matter distribution. So the idea is to reconstruct the dark matter distribution with extremely high fidelity and doing a complete survey of a large field of view with a few million galaxies and getting groups and pairs with no photo redshift cut. You can get an idea. So just show the example. So this is the original simulation. And you can see, so this is the cone, the light cone. And here, this is one example of the distribution of dark matter distribution. I think it's at redshift 0.6 or something like that. So here, this is what you will get with foremost or DAISY. So you can recover the structure, but of course, you're missing the faint source. And it's quite incomplete. Of course, then you say, okay, why not using the LSST? But the LSST is based on photometric redshift, and photometric redshift are not accurate enough, especially for getting groups and pairs. And then you get a sort of fuzzy distribution. So you go very deep, but it's fuzzy. So WST have both the depth and the faintness of the source, and recover most of it. So here from that, you can really recover the dark matter distribution down to Milky Way typical halo mass. And then you can start to connect this with the properties of the galaxy and to see how its evolution will with time with redshift. So I think it's a very interesting thing. Then you can probably play with, it will provide a very interesting constraint on the various dark matter model, for example. And of course, by doing that, you get the large-scale structure, of course, but DFS, it just sits there in the center, and it does observation of deep field, typically what we've done with MUSE a number of times, but we go much deeper with a larger field. And from that, we can expect to show what I've shown, that to recover both, let's say, the small scale structure of galaxy, and you go deeper also, and so you get access to the higher redshift Lyman alpha population, but you can also get the diffuse emission around galaxies and understand all the processes. And you get that for free. On the cosmology side, I think WSC can pretend to be a real stage 5 cosmology survey by extending the current study to a high redshift and larger statistics. And you can see here that the DAISY and foremost redshift range, and here it will be extended to much further redshift with the MOS by selecting different type of galaxy population. And with the IFS, you don't cover such a large field of view, but you have this pencil beam. You provide enough source also to get to high redshift. And so from that, you can infer, of course, the VAO parameter, but of course, gross rate of structure, primary and non-Gaussianities, constraint on neutrino mass, dark energy. And you have people here that know much better than me what can be done with that. And I think it's really impressive what can be done. Yeah, that's another possible survey. It's just an example, where here we will use studies clusters. So there's a dense distribution of a massive cluster in the universe. So there will be a lot that will be found with various surveys. And so the idea is that the FS will probe, let's say, the strong lancing region easily. MUSE has shown that it can really revolutionize this field of view by getting all the redshift and so on to measure the dark matter distribution with a high precision. So you can do that very easily in one go. At the same time, you get the MOS, and this is very interesting because with the MOS, you will get access to the large scale, the weak lancing, and you can try to connect how the large scale connects to the cluster. This is something I think probably new. Time domain is not really a scientific area, it's more a method, but I think it's worth to discuss that a bit because there's a lot of things that will, it's sort of new emerging field, especially with new facility like LSST and later on gravitational wave experiments. And so there are a lot of things can be done. I will not detail all, but people may think that with LSST we can do everything. Let's say imaging time domain capability. Yes, for sure, but if you want to learn to qualify, measure the physics, and even understand what are the sources, you really need the spectroscopy. But if you look, the Einstein telescope will provide gravitational wave event over relatively an area which is similar to the LSST or WST, but in that, the LSST will form, I think, a few thousands of variable events. And to know which one is the real one, you need to have the spectroscopy in relatively short after that of all these potential source, only WST. So we think that WST is also a time domain spectroscopy, ultimate spectroscopic machine that will go together with the other big facility. And of course, we can do many other things like surveying, transient astronomy, stellar variability, because you have the statistics. You know, the key is the statistics. The key is to have multi-scale experiments, and that's, I think, what WST will do. Just to provide a few numbers, I think first computation shows that the MOS in 5 years, just 5 years, will cover 250 million of galaxies, 25 million of stars, down to faint magnitude. The high resolution will cover 2 million of stars still. And the IFS, of course, will cover 4 billion of spectra over a smaller area, but still big enough in various environments. From that, for example, I compute that we accumulate in 10 years of MUSE experiment a few thousand of Lyman alpha emitter. We were really proud to have that. And we learn a lot about science with that. But here we'll get 70 million of Lyman alpha emitter. And not only the Lyman alpha emitter, but the surrounding gas and of the CGM. And this is a complex phenomenon between the CGM and the galaxy. And we can probably help to do the sort of SDSS of the CGM, having enough statistics. Then you can decompose what really are the physical processes that happen in the CGM if you have enough statistics, while if you are limited to a few thousand, it's difficult. And I think SDSS really shows that on galaxies. So there's, with no detail, there's a few challenges, of course. But at the end, it will be much easier than the ELT. First, we use the ELT experience for the telescope. Of course, we have to do massive manufacturing of complex optomechanical systems. So it will be a sort of how to define the process with industry. We plan to develop and use curve detectors that really helps to make the design of the spectra much more efficient and less expensive as well. Check if CMOS can replace CCD, large grating, sustainability, something which is relatively new for us, and we need to look carefully. So develop low energy consumption cooling system, all these sort of things. We are going to look at operation as well. And the operation of multiple servers, we show that foremost is not something easy. So this is something we want to look very carefully, and we can implement multiple surveys over a long time, but still make it able to the community to ingest new ideas and so on, plus the disrupting event that comes from the target opportunity. How to manage all that together is something we have to find a clever solution. There will be huge quantity of data, probably not so huge compared to SK, for example, and so on, but this is the complexity of the data. It's a spectra, it's data cube, and to handle them in an efficient way, we need to require a lot of effort by the community. Cost, of course, it's always a point. We plan something for the concept design to less than 1 billion, we hope. Let's look. A long-term evolution, this is not a facility that is built for 5 or 10 years, it's built for 50 years. So the system evolved, providing access to new science, new ideas, new technology. This is something we want to look at carefully. Okay, so where we are. So this is so we've been lucky to be funded by the Horizon scheme. And the Horizon will start for 3 years in February 1st. And up here, where we'll get all the concept study. And in the same time, ISO has decided to launch a process or to think about what could be the next facility. So this is a yellow scheme. And you see it's well in phase with us. And so that's good for us. And so we have, currently the current plan is that we shall have a full proposal by mid-27 to submit to ISO. And then the ISO approval could be that to see. But it's clear that given the funding and the ELT and so on, it's not for the now. It's not even for tomorrow. It's just the day after. So we're looking for something to 2040s. So that's 15 years from now. And so we have to think about the science, be creative about the science that we can do in this time scale. And this is it. It's just a short summary. Thank you.
Thank you. Questions?